All right. Hello, everybody. So I'm going to start by talking about how machine learning has some issues and how we're trying to figure out how humans learn and apply that to machine learning. So this is a fun little project we did where we wanted to create a Chrome extension that takes all of your Instagram, Facebook pictures and adds a very, very small amount of noise that's imperceptible to you as humans, but totally fools the machine learning algorithm so that it doesn't know that there's a face anymore. And as you can see, all right, I don't have a pointer. So the lines on the bottom here that are going bad really quickly, these are all of the major companies' API of face detection, maybe even one of your companies, unfortunately. And what you can see is that as the noise is increasing, it goes bad really quickly. And the line on top is one of the old school ways of calculating like the distance between the eyes and that kind of stuff. So basically, what we're trying to show here is that machine learning algorithms don't learn structure in a very profound way. And the interesting question is, how do humans learn structure and data? And we're going to talk about a study we did on that. The other interesting question here is, you have these problems that are very, very simple, that are completely fooling even the best machine learning algorithm. So in this case, all you're trying to do is you give two images you give an image to the machine learning algorithm, and then you're trying to tell it, hey, are all the splines in the picture the same? They're just rotated or translated or expanded, right? And they don't do very well. You can see that like most of the state-of-the-art algorithm are 50-50 on that, which is basically random. So how do humans do it? And how do we apply it to machine learning? So the first thing we did here is we ran a very large study with 2,000 mid-career professionals in finance. So these are people who are supposed to be very good at data, at learning from data. And what we do is we ask them to make predictions of assets on the stock market. So SP 500, oil prices, gold prices, these kinds of instruments. And we ask them, what's the price of this instrument in 3 weeks? And we ask all of them to make the same prediction. So that's the number one here. We just ask them, hey, what's the price of this thing in 3 weeks? And then what we do is we show them information. We show them the histogram of their peers. So this is the distribution of what their peers in that platform think the price will be. So this is just the distribution. And then we also show them the actual trajectory, the time series of that asset price over the past 6 months. And then finally, we ask them, hey, what do you think is the price now that you've seen this information? Do you want to change your prediction, or do you want to keep it the same? And if you think about it, this is a very easy Bayesian modeling problem, right? Prior, likelihood, posterior. And this is the data that we have. This is experienced financial professionals, 2,000 individuals. We get 17,000 predictions. We also have their demographics. We also have their grades, because this was part of a MOOC that Sandy was teaching. And we also have some of those rounds of prediction that happened during extraordinary market events. This was not planned. We just got very lucky. Brexit and the Trump election. So this is Brexit. The last day is actually the Brexit vote. And you can see the blue dots here are the futures market. So this is what the futures market is predicting the SP 500 to be. The dotted line is the actual price. And the red line is our crowd. So the first interesting thing is that 2,000 people actually have about the same error as the futures market of the global financial market. But this is not the focus. The focus is, how do they learn from the data? So again, these are financial professionals. We're showing them this data, and we're trying to know, do they use sophisticated models? How do they learn from data? How do they structure in data? Remember, like the kind of motivation here was, how can we learn from data? How can we teach machines to learn from data? How can we understand how people learn from data? So again, what we do is we collect basically this triple of data. We ask them first, what is their prior? So this is when they just show up on the platform. They have no other information that we're influencing them. We just ask them to make a prediction. And then there's the information that we show them, which is this histogram that we also record. And it's different for every person. Because as they're making predictions, the next person who comes in, there's basically new data on that histogram that we're showing them. And then we can see their revised prediction. So first of all, the simplest model you can come up with of how people are updating their belief is this super simple Bayesian model, which is their revised prediction is just the average of the data that they saw. So it's the average of their prior belief, and then the average with the histogram that they see. The simple model, you're just adding those two numbers. So you're adding, again, the prior belief, the mean of that histogram, and then you divide by 2. This is the simplest model that you can come up with. Other than, I don't know, a completely flat model that is not informed by anything. But we're hoping that those financial professionals don't do that. The other kind of models that you can do is something much more sophisticated, where you're doing like a numerical binning of how each bin corresponds to their prior belief, and then you're integrating over the whole space. So the first question is, what do those financial professionals do? Do they use the super simple model, or do they do something much more sophisticated that's basically numerical analysis? And interestingly, what we see is that they use actually the simplest model, which is very surprising, kind of shocking actually. So these are the different rounds, these are the different models, and every time you see a much lower error of predicting what people are actually, how they're updating the belief, this is actually the super simple model, where you're just taking my prior belief, adding to the mean of the histogram, dividing by 2, and that's my updated belief, which is kind of shocking that these financial professionals are doing that. So then the next question is, all right, so what about in terms of data source that they're using? Again, using this super simple model, what you can do is you can say, all right, are they using the time series, or are they using that distribution of their PS belief? You would want them to use the time series, because that's what efficient market hypothesis is telling you how you should update your belief, right? Because all of the information of the market should be factored into the price. However, these 2,000 financial professionals, turns out, just use the histogram of the PS belief instead of using the time series, right? They have no excuse, because they've done that for a long time. So very interesting, right? Like, as humans, we tend to prefer listening to our peers. At least this is what this study and this data is saying, compared to learning from the actual price series, right? But what does that mean? Why are we doing that? Like, why do we prefer our peers versus preferring to learn from the raw data? So there's actually reason to the madness, and this is the reason. So in this case, what we're doing is, because we have such granular data of those 2,000 people, what we can do is we can subset them. We can say, all right, so this group learned mostly from the histogram of their peers, and this group learned mostly from the data, or this group learned from a balanced usage of those two data sets. And what you can see here is that as people, so each point here is a subset of the population compared to the whole population, right? So we're trying to see, how does a subset that learns from a specific type of information compares to the crowd? And this is the improvements compared to the crowd, and this is the standard deviation of improvement. So you can basically think of that as, risk and reward, or, mean and risk of the returns. And what you can see here is that as people learn more and more from their peers, their improvement compared to the whole crowd is slightly smaller, but their variance, their risk is actually much, much smaller. So when you learn from your peers, what this is saying is that you might do a little worse, but you're actually more certain statistically. So there's less variance, there's less deviation, there's less volatility in your prediction. And then when you learn from just the price of the price series, the time series of the price, what you're getting is actually a slight improvement in line with the efficient market hypothesis, but it's higher volatility. So you can see it's a very clear Pareto, trade-off between what you're learning from. So this is the last part of this one study. We also applied that to 1,000 online prediction markets. So this is Cycles. This is a very well-known prediction market. We applied the same idea here, which is, how can we think about how people are learning from each other and use that to make the market more efficient? And this is what you see. I'm not going to go into the math, but basically we have a very useful model that tells you just from time series how much are people being influenced by each other. And then what we can do is we can do the same thing where subsetting people based on how much they're listening to each other. So that's kind of like on Instagram, how much am I looking at other people's profile. And what you can see here is that, as you listen more to your friends, you actually get a slight improvement, but then it kind of crashes down. So there's always this kind of Pareto trade-off between listening to people versus listening to the price. So you want to be somewhere in the middle. So that was study one. So the other study, part.
Just stop for a second.
Yeah.
So you folks understand, right? So all of economics is built on the efficient market hypothesis. What this is saying is you can actually get something like a better Sharpe ratio by paying attention to other people, so you're integrating information more broadly. And this, again, gives you sort of a mathematical way of doing this as opposed to what people do, which is just heuristic. And these are, mid-career finance people making financial predictions. So there's like no excuse. And the improvement is actually sort of substantial, and particularly for volatile situations.
When you say paying attention to other people, when you say paying attention to other people, how are you getting that data?
So
You mean exactly by that?
right. So what we mean by that is we can calculate the error in the model of how much you're using different kinds of information. Because what we do is we can calculate in a model that is only using the price history, you get a certain error, and then the model that's only using the social histogram, you get a certain error. And then by comparing these errors, you can say statistically, people must have learned more from the price data versus from the likelihood. You can only compare these two things.
It's price history versus what everybody else is doing.
How are you learning whatever?
So you show them, you ask them to make a prediction, and then immediately you show them what everybody else is doing,
Right.
and you show them the price history. It's a contained
Exactly.
experiment.
It's like an A/B
they
test.
re-estimate the price, which gives you the ability to know how much they were influenced by those two pieces of information, which are different. And what you see is people are influenced by both pieces of information, and the ones that have, in some sense, this better Sharpe ratio, it's not quite a Sharpe ratio, are the ones that integrate both sources of information, not the ones that do just the price information. Right? And then you can back that out in situations where it's uncontrolled, because now that we know that, we can go to another market, a true market, right, and be able to say, is there a subset of traders which show the correct behavior, and in fact, those are better than the other traders? Okay? So we can come back to this and do it at lunch, because this is one of these like, I have to think about that type of things, right?
There's no bias here.
It's a way of backing out what the bias is and getting rid of it.
Yeah.
Okay? And also one of the things, he showed the thing got a little better and then it went down.
Yeah.
So this is avoiding herding effects.
Quick
We're
question.
going wrong, yeah.
Sandy, you made the first point that the social exposure influences the decision or the learning. I thought also it's the trend line, which the data shows what it ought to be, has a lot more influence on the predictability of the future, more than the social.
So he showed that the trend line actually results in better average accuracy, but higher volatility.
I see.
This is the humans looking at the trend line
Yeah.
and saying, what should I do?
Yeah.
And the humans that look at the trend line and look at what everybody else is doing and blend those two have a very nice trade-off between accuracy and volatility in their estimates.
Because the application that was going through my mind is tail risks. Most people, when there's social beliefs, there's a noise signal. There is a signal in there, but people are just herding it into one
So this
conclusion.
is also a way.
Whereas there is a signal on higher tail risk coming up, which people are ignoring.
Right. So this is a way to avoid that tail risk also. That's the other side of it, right?
Right.
Okay. A little bit of improvement, much better way to do tail risk. Okay.
Keep going?
Yeah.
All
You
right.
have to be quick.
All right, I'll be super quick. So the second part of this talk is about deep learning, which you might have heard about. So the interesting thing is if you look at most deep learning right now, you are starting to see distributed architectures of learning. But the interesting thing of how these distributed architectures are organized is actually in a very naive way. So what you have is you have a bunch of different workers, and they're all doing learning using the same, slightly noise parameters, and then they're all sending it to some controller like the mothership that's doing the update. So it's very naive. It's what we call in social science a complete network. Each of the nodes are communicating with all the other nodes, and that's not very efficient if you're searching a space, which is essentially what deep learning is. You're searching the landscape for better parameters that give you lower validation error. So what we do here is we take inspiration from how humans are organized in networks. So this is one of our big studies. This is eToro, and then we have now data from DarwinX. These are social trading platforms where people create profile like Facebook, but then they trade. So they do useful stuff. And the interesting thing here is that the structure of the network, I'm not going to go into the details, tells you a lot about the performance of not just the individual users, but the collective network, the collective market. So how can we apply that to these distributed deep learning structures? So the idea here is to take this fully connected network where all of the nodes, all of the workers are just using the same parameters, just searching the space in parallel, and have a more natural kind of organic network. So what we do here is we take one of the big scalable deep learning architectures, what this one is called evolution strategies. The only reason we use it is because it's very scalable. You can run thousands of workers at the same time. Most deep learning architectures can only run maybe 10, maybe 20, maybe 30. So we use the same idea. So think about how you have basically a population of workers that are searching this landscape in super high dimensional space. And the idea here is, can you have a sparser network where you have little groups? It's kind of like brainstorming groups, right? You have different groups of people that are in different rooms that are searching for the same solution. The idea is that this would be more effective. So what we do here is we use canonical, networks from social science. So this is fully connected, which I just described. Erdős-Rényi is another one. I'm not going to go into the details of the math. Scale-free is really interesting. Small world is, the 6 degrees of separation. So we take those very, very simple canonical networks that come from social science, and we just take these standard state-of-the-art deep learning algorithm, and we change the network. So that's the only change that we've done. And first, we have some empirical results, and what you can see is that the fully connected networks, which is literally what everybody uses, Google, Facebook, whatever, and it's actually the worst, right? And then we try different types of networks, and Erdős-Rényi ends up, all of them are better. Some not very significant, but Erdős-Rényi is statistically significantly better. And then we run those with different number of agents. And what you can see is that 1,000 nodes, 1,000 computational nodes that are running deep learning, using Erdős-Rényi network can do as well as up to 3,000, 4,000 agents in the classical common way that everybody is doing, which is using a complete network. And the kind of benchmarks that we're using here are state-of-the-art hard benchmarks, which are those silly walking robots. And what you can see is that the improvement ranges from 10% all the way up to almost 800% just by changing the social network. So again, the theme has been, how do humans learn from data? Because clearly, evolutionarily, we do really well. We're able to solve some very complicated problems, and how can we apply that kind of thinking to learning from data, whether it's distributed, whether it's financial professionals.